if I let my joint PDF equal 1 over y, and even though this only depends on y, over here I am going to put in of x as well. X doesn't affect the output of this function in the formula. But it is something to think about with respect to the domain. Over a domain, the points x, y are going to vary over a domain. I'll call the domain R for region. I could call it D for domain. Well, maybe I shouldn't call it R because it's not a rectangle. Sorry. I'll call it D for domain. That is the set of all points in the plane satisfying the condition that 0 is less than x is less than y is less than 1. What in the world is this set? You're a little used to set building notation. This is the set of all points such that these inequalities are true. If you've never seen this before, this symbol means is an element of, or I just say in for short, is an element of. That's the official way to say we're talking about points that are in this set. But what is this set? Just looking at these inequalities, it's challenging for people to tell what kind of set this is. But it does turn out to be a triangle. Here's x, here's y. Do notice that both x and y are between 0 and 1. So somewhere, it's a triangle somewhere in this box here, in this square. I want the x coordinates of the points that I'm considering to be less than the y coordinates. Y to be bigger than x. Where is that going to happen? It's going to happen when you're kind of up high, when y is higher than x. When you're above the line y equals x, there's the line y equals x. The points above that line in this triangle are going to be the points in this domain. That triangle right there, that is D. Oftentimes we call it R for region as well, but R also is the first letter in a rectangle, so I didn't want to do that. It is not obvious by any means that this is a PDF over this domain. That's not obvious. That's something we'd like to verify. Assuming it's true, assuming it truly is a PDF, that it's going to, the double integral of this over this domain equals 1, it certainly is positive, not negative over the domain. By the way, it is going to be 0 elsewhere. It is technically piecewise. It's 0 otherwise, but I won't bother about the otherwise when I do my calculations. Assuming it does integrate to 1, can I do all the things you've done so far? Can I find the marginal PDFs? Can I find the expected value of x, the expected value of y, the expected value of x times y, and therefore the covariance? Can I find the correlation? Yes, you can do all those things. We're going to do more today. We're also going to find something called conditional PDFs and curves of regression. The conditional PDFs and the curves of regression are the hardest part, but I think they're also the coolest part. Let's find the marginal PDFs first. How about the marginal PDF? We're going to do the marginal PDFs. There's 2 of them. How about the marginal PDF of x first? What's the definition of the marginal PDF for a continuous random variable? You integrate the joint PDF with respect to y if you want the marginal PDF of x over all values of y. I could write a minus infinity to infinity there. I wrote an all y. It's not a big deal. To actually do the integral, though, we need specific limits of integration. We are integrating ultimately 1 over y dy. But what are the limits of integration? It's tempting to think that they are 0 to 1. But no, they're not. And this is the trickiest part right now. What you want to do is you want to say to yourself when you look at this, since the integral is with respect to y, when I do the integral, I want to think of x as fixed. Of course, in the end, you'll get an answer that depends on x, and so that could then be thought of as a function of x. But while you do the integral, you want to think of x as fixed. This is very important conceptually. What is x? It doesn't matter. Somewhere between 0 and 1, you can pretend it's there. The limits of integration for y depend on what x is. If x happened to be 0, y would go from 0 to 1. If x happened to be 1, y would go from 1 to 1, right? Just 1 point up there when x is 1. If x is a half, I guess y goes from 1/2 to 1. Whatever x is, y goes from the second coordinate of this point to the second coordinate of that point. Now, the second coordinate of this point is easy. It's 1. But what's the second coordinate of this point? Its first coordinate is x. What about its second coordinate? Y? Well, yeah, for that line, it's y. But we want, when we do this integral, the y's to go away. I want the second coordinate of that point in terms of x. And since it's on the line y equals x, it equals x. For this fixed value of x, y varies from x to 1. Those are the limits of integration. It's okay to have a variable limit of integration here as long as it doesn't depend on y. When you do the integral, pretend x is fixed, though. Integrate 1 over y, we've got natural log of the absolute value of y plus c. Do you really need the absolute value signs here? No, because both x and 1 are positive, so I won't bother with the absolute value signs. Looks like I get natural log of 1 minus natural log of x. Natural log of 1 is 0, so this simplifies to negative natural log of x. A negative number? How can that be? Well, keep in mind x is between 0 and 1, so this is actually a positive number. Right? Log of a number between 0 and 1. Think about the graph of log. Log of a number between 0 and 1 is negative. So negative of that is positive. That looks like, if I haven't made a mistake, the marginal PDF for x. What does its graph look like? It'd be the graph of negative natural log of x. Take the graph of log of x between 0 and 1 and flip it across the x-axis. I guess it looks like this, and I guess it would have a vertical asymptote. Is that right? Yes, it is. This is actually correct. PDFs can have vertical asymptotes as long as the integral over the entire domain converges. We should probably check that this integrates to 1, though. And that would be, if we can do that, that would be a check that the double integral of the joint PDF integrates to 1, because when you find this marginal PDF, you've really done the inner integral, at least with respect to y, of the iterated integral. We've just done the inner one. If I'm going to integrate this from 0 to 1, I need an antiderivative of natural log, which is not obvious. That's probably another side calculation here. Antiderivative of natural log of x. And, well, integration by parts is the best thing to use to figure it out. Really? Our textbook uses v prime. Other textbooks use dv. What should u and v prime be? Turns out best to let u be natural log of x and v prime be 1. This integrand is natural log of x times 1 as well. You want the product of u and v prime to be the integrand. If you wrote it in terms of dv would be dx. I'm not sure which integration by parts formula you're more used to, but if you took calculus here, u prime is 1 over x. Another way to say that is du is 1 over x dx. V, the integral of 1 is x. So the integration by parts formula says uv minus the integral of v du, or v times u prime if you prefer, multiply these two things, uv, get x natural log of x. V du means multiply these two things as well, and the x and the 1 over x cancel to give you the integral of 1. So we get x natural log of x minus x plus c, but then we won't need the c because we're going to do a definite integral. The c can be 0. So that's all prep work to help me do this integral here. It's really an improper integral as well, because of the vertical asymptote here. So really, if I want to be extra technical about it, I should write it as a limit. As the lower limit, call it a, goes to 0 from the right of the integral from a to 1 of negative natural log of x, being an improper integral. Some improper integrals are where you have, infinity in the top limit of integration. You're letting the top limit of the integral go to infinity. You want to know if the integral converges or not. It's not obvious that this converges. And actually, even when I use this antiderivative, it's still not completely obvious. I got the negative sign there as well. I need this antiderivative. This is 0 there. I need this antiderivative with a negative sign involved. Negative x natural log of x plus x. X going from a to 1. All right, we're getting close. Limit as a goes to 0 from the right. Plug in 1. Subtract what you get when you plug in 0, or plug in a, excuse me. Don't make a mistake. ln of 1 is 0. This becomes the limit as a goes to 0 from the right of 1 plus a ln of a minus a. That goes to 0, but what about this? Question mark, question mark. A is going to 0, but ln of a is going to minus infinity. What is the product going to? It's not obvious. Calculator, graph x times natural log of x close to 0. Looks like it's going to 0. Yes, it is. It's no proof. So in the end, we approach 1 like we should. Not a proof. If you were to prove this a bit more rigorously that this goes to 0, what could you do? You could technically use L'Hopital's rule with a bit of a trick. It's a 0 times infinity indeterminate form. Okay, I might as well do it. Limit as a goes to 0 from the right of a times natural log of a. To use L'Hopital's rule, you got to write that as a fraction. Really? Yeah, write it as natural log of a divided by 1 over a. Bit of a trick. Now it's an infinity over infinity indeterminate form. When you do that, and you can use L'Hopital's rule, thinking of a as a variable and differentiating with respect to a. L'Hopital. Derivative of natural log of a is 1 over a. Derivative of 1 over a is negative 1 over a squared. But wait a minute, isn't that still infinity over infinity? As written it is, but it can be simplified to just negative a. And that limit is 0. Oh, so much math coming together in one problem. Of course, you could say, well, did you ever prove L'Hopital's rule? We never actually proved L'Hopital's rule in calculus. We just used it. Proof's actually kind of subtle, but it is true. Where were we? What was this all about? We were trying to verify the integral of this from 0 to 1 was 1, and we did. Okay, that verifies this is a valid joint PDF. There's the inner integral of your double integral to get this marginal PDF. Then we integrated the marginal PDF and got 1. So the double integral equals 1 as well. This going to be on the test? Maybe with some help. There could be a problem similar with some help, maybe. Yeah, it's very easy to make a mistake. So I'd want to give you some help to help avoid mistakes. Help make the grading go better too. Help you do it in a good amount of time. But for the moment, you can do it completely from scratch. How about the other marginal PDF? We haven't found the other one yet. F sub y of y, integrate over all x, the joint PDF, with respect to x. Integrate 1 over y dx. Really? Yes. But what are the limits of integration on x? Go back to your picture. There's d. Now you want to think of y as fixed. Somewhere between 0 and 1 when you do this integral. And for a specific value of y, x varies between the first coordinate of this point and the first coordinate of that point. That point is 0, comma y. This point is y, comma y. For this specific value of y. Focus on the first coordinates. You want to go from 0 to y. Take some practice. You don't want to do this on the exam without some practice. Integrate with respect to x. You don't see an x. Well, treat 1 over y as a constant. So if I integrate that with respect to x, I guess I get x over y. X going from 0 to y. Which gives me then y over y minus 0 over y. 1. For y between 0 and 1. It's uniform distribution. The distribution of y is uniform. If I don't know what x is, and just thinking about how does y vary, not thinking about x, this uniform distribution models the variation in y. The variation in x was not uniform. It was like that. You're much more likely to have small values of x than large values of x. If you just focus on the observed values of x and ignore y, you're much more likely to have small values of x. The PDF's much higher, goes to infinity, in fact, as x approaches 0. All right. Let's find expected values now. All right, how about the expected value of x, first of all? I've got to use the PDF of x and multiply times x. I guess I got to do this integral. X going from here, I do want to think of x as going from 0 to 1. I'm sort of ignoring y here. That's the marginal PDF of x there. That integral can be done by parts as well. Let's start using technology now to save some time. It can be done by parts. You want the indefinite integral of x times log of x. You'd want to let u equal ln of x and v prime be x. Turns out you still want to let u be ln of x. You don't want to let v prime be ln of x because then you're trying to find v and you'd be trying to, yeah. There it is. The definite integral of that from 0 to 1 with a minus sign in there should be the mean of x. And by the graph of the PDF for x, it should be closer to 0 than it is to 1, right? Much more likely to have small values. So this should be close to 0. 1/4. Okay, yeah, closer to 0 than it is to 1. So we'll just write that down. We use technology to figure out. And you could do it. You might want to do it on your own. Looks like the mean is 1/4. Mean of y, integral of the PDF of y times y. PDF of y was 1. Hey, that's easy to do. 1/2 y squared going from 0 to 1. 1/2, oh, it makes sense. Y is uniform on 0 to 1. Means halfway between 0 and 1. Before we find the covariance, let's also find the variance of x and the variance of y. Variance of x, integrate x squared times negative ln of x. So this will be the second moment. So I said that wrong. I said variance, didn't I? I want the second moment. 1/9. That's the second moment of x. Its square root 1/3 would be the standard deviation. So x has a mean of 1/4 and a standard deviation of 1/3. The variance of x then would then be 1/9 minus 1/4 squared. Variance of x is 7/144. You want to write that down? Maybe check it on your own. Variance of x. Variance of y. Do I remember the variance for a uniform distribution? Wasn't it b minus a squared over 12? I think it was. B is 1, a is 0, 1 minus 0, 1 squared 1 over 12. Variance of y should be 1/12. Second moment of y, double checking. 1/3. 1/3 minus 1/2 squared is 1/3 minus 1/4 is 1/12. What about we're after the covariance here? Remember the covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y. So we got to figure out the expected value of x times y. To do that, you'd have to do a double integral. This would be the double integral of x times y times the joint PDF, which was 1/y, over the entire domain D. dA is the way you write this in the abstract. The y's cancel, so you are ultimately just integrating x. And it doesn't matter whether you do it with respect to x first, then y, or vice versa. Should get the same thing. It is possible that one way is easier than the other. I don't know offhand which way is going to be easier. I'll imagine doing it with respect to x first, then y. So the integrals with respect to x first, thinking of y as fixed, that's analogous to what I did up here. The limits of integration have to be 0 to y. And y ultimately goes between 0 and 1. So this integral should give us the second moment, or not the second moment, but the expected value of x times y. Would it be difficult to do by hand? I would get x squared over 2, x going from 0 to y, giving me y squared over 2. I'd have to integrate y squared over 2 from 0 to 1. It would not be too hard. One-sixth. It should be the same answer if I do it the other way around. With respect to y in the inner integral, let x go from 0 to 1 in the outer integral. Let y go from, just like before, x to 1. Function's still the same. We're still integrating x. This calculation right there is still the same. x times y times the joint PDF, and the y still cancel. So I still integrate x. Should give me 1/6. Yep. So the covariance is 1/6 minus expected value of x times expected value of y. Was that 1/4 times 1/2, right? 1/8. The covariance looks like it is 1/24. Positive. Slight positive covariance. The correlation gives a better scaled estimate to help you interpret the true strength of the relationship between these things better than the covariance does. The correlation, if you recall, is the covariance divided by the square root of the product of the variances. Remember that? It's in the book. Page 170. This was what we call rho. I'm forgetting. The variance of x was what? What did we get? 7 over 144. And the variance of y was the 1/12. Yep. So square root of 3/7, which is about 0.655, is the correlation. Might call that a moderate correlation. Halfway between 0 and 1, close. Actually, we'll see, or more likely you'll see in applied statistics, if you take that it's the square of the correlation that is a better measure of the strength of a linear relationship. Doesn't measure strength of nonlinear relationships, it measures strengths of linear relationships, which we really don't have here. What we now want to consider is one more new kind of thing in chapter 5. The idea of a conditional random variable and curves of regression. This really gets wild. We want to consider, for example, the values of x if we happen to know the value of y, conditioned on knowing the value of y. Oh, how about writing the random variable like this? Wait, really? This is one random variable here. One random variable. That whole symbol represents one random variable. The random variable representing the conditional value of x given that the random variable y equals little y. Our book uses a shorthand notation for this that gets rid of the capital Y. Textbook shorthand notation. But to tell you the truth, even though it's quicker to write, I prefer the longer notation. I don't always use it, but I prefer the longer notation. What is this? Well, as always, you got to describe a random variable by the functions associated with it being continuous by a PDF. What is the PDF? The conditional PDF. F sub capital X given capital Y equals little y. And again, our book uses the shorthand notation and just writes a little y there. It's the PDF for this random variable. What is its variable? Is it X? Is it Y? Is it both? It's X because I'm trying to model a value of X. This is a conditional value of X given that you happen to know Y takes on a value little y. So its PDF should be a function of little x. But in the formula I'm about to write down, the formula has got to involve little y in some way because that's what I'm given. And it does. It's the ratio. Oh, not surprising. It's conditional. It's a ratio of the joint PDF value at x comma y divided by the marginal PDF value of y at little y. And this thing, when you look at it, you should say to yourself, this is a function of x, even though there's y's in there. Because you're thinking of the value of little y as given, as fixed, as constant. And so, yes, you do need that value of y to figure out this formula. And the formula, if you're letting y be arbitrary, will depend on y. But I'm mostly thinking of x as the variable when I look at this. Likewise, there's a conditional PDF the other way around. Conditional PDFs. The other way around is going to be the joint PDF or conditional PDF of y given capital X equals little x, and this is going to be a function of little y. The numerator will still be the same, the joint PDF. It's the denominator that changes. These ratios are meant to be analogous to ratios defining joint probability or conditional probabilities back in chapter 2. In fact, if the random variables x and y are discrete, it is the formula from chapter 2. Because this is the conditional probability of A given B, say. That's the probability of A and B. A intersect B. This is the probability of B. It's the exact same formula as in chapter 2 if x and y are discrete random variables. But you still use these formulas even if x and y are continuous random variables. Here is the joint PDF. 1 over y. The marginal PDF of x was, that was negative natural log of x. The marginal PDF of y, that was the constant function 1, when y is between 0 and 1, it was a uniform distribution. So the conditional PDF of x given y equals y, how should I type this in? Given, I'll just say given y, make a subscript here. How about this? Of x. Can I do that? Yeah, you can. It's the joint PDF divided the marginal PDF of y, which is the constant function 1. So this formula is going to be the same as the formula for the joint PDF. It's going to be 1 over y. And if I type this without the underscores, it'll spit back the formula at me, hopefully. Yeah, 1 over y. But remember, this is a function of x. Y is, you want to think of y as constant. But what constant is it? Y could be different numbers between 0 and 1. So I guess this is different conditional PDFs of x for different y's. Yes, it is. But how can that always integrate to 1 no matter what y is? As long as you get the domain. For this example, the conditional PDF of x given capital Y equals little y of x equals 1 over y, not for x between 0 and 1, but for x between 0 and y. Go back to the triangular domain. For any given y between 0 and 1, any fixed y, x varies between the first coordinate of this point and the first coordinate of this point, 0 and y. Again, this point has coordinates 0, y. This point has coordinates y, y. First coordinates are 0 to y. And it's got to be that way if this is going to integrate to 1. This is going to be a PDF. How do you check that it integrates to 1? You're integrating with respect to x. From 0 to, not 0 to 1, but 0 to y. Getting x over y, x going from 0 to y. Getting y over y minus 0 over y is 1, no matter what y is. I mean, we do want y to be positive, otherwise that's undefined. What's its mean? Mu sub x given y equals little y. And in general, that mean is going to depend on y. Integrate this conditional PDF 1 over y times x, not y. Integrate with respect to x from 0 to y. I put the x in the PDF in the opposite order as usual. This is f sub x given y equals y of x. I'm integrating x times the PDF of x, even though it doesn't involve an x. What's this going to be? What's this going to be? I'm integrating with respect to x. I'll get an x squared over 2y. X goes from 0 to y. That's going to be y squared over 2y minus 0. Simplifies to y over 2. Yeah, that makes sense. This it's a uniform distribution. That's a constant. Constant when y is fixed. The PDF of this random variable here is constant at 1 over y as x goes from 0 to y. And its mean is going to be y over 2. But it does depend on y in the end. This is a function of y. It's called the curve of regression of x on y, I believe. Curve of regression of x on y. What does its graph look like? Graph it as a function of y, meaning graph it sideways. Huh? Treat the vertical axis like it's the independent variable. What will that graph look like? It'll look like this. Thinking of the vertical axis as the independent variable, the graph of y over 2 will look like that, a straight line with a slope of 1/2 when you turn the graph sideways and look at it in a mirror. I'm serious. Look at it in a mirror. Do this on your own. Turn it sideways, look at it in a mirror. It'll look like an ordinary graph with a slope of 1/2. Here it's a backwards graph with a slope of 1/2. That should make sense. For any given y, the mean of x is halfway between the extremes. Does the same kind of thing happen with the mean of x? Or the mean of the variable y given x equals x. Does the same thing happen? Let's see. Copy and paste this stuff and change the variable names around. Make this fx of x. What's the formula for this one? Oh, not uniform. X is fixed when you look at that, but there's a y in that formula in the bottom of the fraction. Not a constant function. It's got a vertical asymptote at y equals 0 at least, but does y go to 0? No, it doesn't. That's good, because the integral of 1 over y from 0 to 1 diverges actually as an improper integral. This is the formula for this conditional PDF as long as y is between x and 1. Back to this picture. Imagine a fixed value of x. Y goes between the second coordinates at these points, x and 1. So the mean, the curve of regression here, the mean is going to be the integral of this of y times, oops, y times this thing. Let's just copy and paste this in here. dy, y goes from x to 1. And that's going to, in the end, depend on x. And it will not be a linear function of x. Is that? Yeah. What does the graph of that look like? And could you do it by hand? Yeah, you could cancel the y's. Log is in the... Well, you're integrating 1 over log x, negative 1 over log x with respect to y, so it's easier than it looks. The log in the bottom just stays as is. You get a y over ln of x. What does the graph of this look like? It's not linear. It's curved. Back in this picture, this curve of regression of y on x, well, let me redraw it. Looks like, is it in the triangle? Yeah, I mean, if we made the axes same ratio. Yeah, it is above the line y equals x. So this curve is in here. That's the graph of the mean value of x. No, excuse me, the other one. The mean value of y given x equals little x as a function of x. What's that telling you? For any given x, if you know that value of x, the output of this graph tells you the mean. And it's not halfway between the extremes. It's not a line like this, because it's not a uniform distribution. The mean increases very rapidly as x increases from 0, and then doesn't increase so rapidly when x is close to 1.